In this class today we will study the operational amplifiers. Operational amplifier is nothing but basically a direct coupled high gain amplifier which consists of a differential stage and in between a middle stage called a translation level stage and an output stage. The output stage consists of a parallel push-pull amplifier or a symmetric of the amplifiers. All these inside are in one IC. So the operational amplifiers are available in the integrated circuit called IC form. The basic operation amplifier can be used as one of the tool in any of the electronic circuits. To design any electronic circuit, the basic operation amplifier can be implemented to work it as in any of the fashion they like a rectifier, like a summer, integrator, or any of their own choice of their circuit requirements. One thing is that all these operation amplifiers are available in the IC form, which consists of number of stages inside. So for the user it is nothing but integrated circuits. That integrated circuit is available in three types of the forms. One is called your metal can, which is TO5 case, and that has got 8 pins, and the second type of IC available is called the flat top, which is 8 or 12, and the third is the DIP line. Either 8 lines or 8 pins are called 16 pins. Any of the type is available, can be in one or called the dual op amp available. This is manufactured by not only Fairchild and National Semiconductors, but also many of the companies like RCA, Texas, Signetics, and every of this has got a last suffix numbers digits called 741. The forward can be any of the number depending on their company's pro forma or their profile, but the last 3 digits called 741 which gives a operational amplifier which is called the basic operational amplifiers. Now today's class, let us see that how they are available and what they are meant for and what are the specifications they have to stand for and what is their behavior in the electronic circuits. Now looking at this, they are available in the 3 forms are called under the grades. One is called the military grade called mil grade, second is the commercial, third is the industrial. The mil grade is one in which each of these 741 are called operational amplifier will work from minus 55 degrees to 125 degrees, and in industry grade minus 20 degrees to 85 degrees. In the commercial grade it is available from 0 degrees to 75 degrees. Now looking at this, what is the basic operational amplifiers, also known as op amp. The op amp, which I said has got inside 3 stages at least minimum called differential inputs and a level translation stage, and third is the output stage. So now it has got certain specifications. What are the specifications now? Let us see. The first one is called your, if you see the basic block diagram operation amplifier, which is represented like this fashion and has got its terminals called the inverting input and non-inverting input, and the output terminal which is the OBP indicated here. The inverting in the sense here, the signal is whichever you give here it will get out of the phase, and that's why it is shown as a negative sign. Non-inverting in the sense is that what is the input you are giving here, it will be by multiplying some constant either the gain or called K, and output is available without any change in the phase shift. The basic block of this is given as here in this fashion with a power supplies called plus VCC and minus VCC. This is meant for drive the inside circuit, which I said already the blocks are there inside the op amps. And plus VCC means plus of the voltage can be from plus 12 or 13 or 14 or 15, maximum is 15 volts. Here minus VCC, in some cases they write as VEE. VE or VCC what it may be, but the sign is a negative voltage. So you can connect here plus 15, you can connect here as a minus 15. The output is taken from this. If I take the particular reference of the MU741, this will be 6 pin, this will be a 3 and a 2 and then 7 and 4 etc. respectively. Now this is the symbol of your basic operational amplifier used in any of the circuits. Now let us go to the characteristics or specifications, how they decide and how they determine the behavior of this. One is called your input offset voltage. What is the input offset voltage? That is nothing but the reflected voltage or the output for a given input differential voltages. The differential voltage here is nothing but your VDC1 and VDC2. If I apply DC voltage, of course basically the operational amplifier will work not only for the DC also for the AC signals, and here in this case whenever the DC1 is applied to this pin called non-inverting, and to the inverting input called VDC2, then the output will be your reflected V0 or called VIO is equal to the difference of these voltages. So basically as per specifications, this input offset voltage VIO must be very minimum as equal to theoretically 0 value, but for a typical case of this, if I take here is equal to 6 millivolts. For a precision operational amplifiers, it has to be less than 50 nanovolts or microvolts. Then here in this case, the second is called the input offset current. Similar to this, what is the current flowing into this terminal called inverting input terminal? Similarly, the current which is flowing called IB2 into the non-inverting input terminal. The difference of this algebraic sum difference are known as the difference of these things. If I take it here, we produce a called offset current. That means instead of flowing in the output here, any of the difference, anything is there which will reflect in the output is called your offset current. That offset current has to be theoretically 0, but it will be in the order of 200 nanoamperes for a 741 IC. And next is the input, also known as the differential input resistance. This is the resistance measured here at the for the value of given voltage or current, and the difference of this resistance which is between the terminals, input terminals, is called your RI, and this will be order of tens of mega ohms. For a particular mu p say R called your mu S741, it will be 2 mega ohms, and for any of the standard precision amplifier it will be greater than 10 mega ohms. The next is input voltage range. What is the input voltage range you can give? That is nothing but here when you are giving a same voltage to both the terminals called inverting and non-inverting. Both the terminals, if you give the common voltage, then the operational amplifier is said to be working in the common mode operation. Under the common mode operation, for a given value of the plus supplies called plus VCC 15, minus VCC is also called minus 15. Under these conditions, the maximum voltage which you can apply to this is called your input voltage range, nothing but plus or minus 13 volts, which is nothing but VCM. Then the next is characteristic of output resistance. The output resistance of this operational amplifier, whatever I take here, either 741 or any of the company's name here, particularly it will be very small, order of 75 to 80 ohms, and that is the basic characteristics of an amplifier, that it has got a tremendous value of the input which cannot load any of its previous stage, and it has got a very small resistance which has got the best characteristics that it can drive the following circuits. Then let us see the other characteristic called your CMRR, which is one of the best quality to be measured in the case of an operational amplifier. So what is the CMRR? It is called common mode rejection ratio. The common mode rejection ratio is nothing but the ratio of the differential gain divided by the common mode gain. This common mode gain is nothing but when you are applying a voltage signal of this nature called a common mode operation, then its value will be V0, output voltage in the common mode, divided by the input voltage in the common mode. Generally the value of that will be always less than 1, and whereas here a differential voltage is nothing but your voltage gain, which is called also large signal voltage gain. For a theoretical value, the value of this one will be 200 kilo, that means 200,000, you can take it as 2 followed by 5 zeros, which is a very large value. So hence if I measure here, CMRR will be order of 90 dB for a typical value of 741 IC, and it can exceed better than this value for other precision operational amplifiers. A typical value is 90 dB is a very high value, which will indicate that the performance of this, nothing but the matching of the input terminals, is exactly correct as per the theory. Then the slew rate. What is the slew rate? Is nothing but the response of an operational amplifier which produces in the output for a given change in the input. Once again I repeat, a slew rate is the one which is nothing but the change in the output, or called the rate of change of the output voltage for a response of the input with respect to time or unit time. That is, SR is defined as dV0 by dt. That is the maximum value for which of the time or the voltage, and it is expressed in terms of volts per microsecond. It is expressed as volts per microseconds. Generally it is specified at the unity gain. Then we have seen already the block diagram of, or the block or symbol of these operational amplifiers, and then let us see the equivalent circuit, how it is defined. Now coming to this figure, it is called equivalent circuit of an operational amplifier, which has got two terminals, nothing but plus and minus. Plus is called your non-inverting input terminal and minus is called your inverting input terminal. And the equivalent circuit, when I saw, that means when I look into the block of this inside, what it consists of is called your equivalent circuit of the operational amplifier. That consists of, in between these terminals, a large value of resistance, which I said Ri. Ri will be order of the 10 mega ohms. So it consists inside the block is called Ri, whose terminals are brought as two input terminals, inverting and non-inverting. Then with respect to the output terminals here, when I look back, here it is nothing but equivalent to a voltage generator, whose A is nothing but a large signal gain, whose value will be order of 20 or 200,000 and multiplied by your VID. What is the VID? VID is nothing but the voltage existing between these two terminals called your differential input voltage, known as VID. This VID in turn will be a very, very small value. So VID will be, say, if I take order of say 0.1 volt or 0.4 volts and the 1000 of the gain is there, then it becomes 8 volts. So you can imagine that the larger the gain is the property of this operational amplifier, which is standing for A. And this A into VD is nothing but equivalent of the voltage generator inside with a output resistance R0, which we have specified that output resistance R0. So therefore R0 will be of the value of the very small, less than 100 ohms, typically 75 ohms. So this is the equivalent circuit with which of course plus VCC and then minus VCC also is there here. Now let us see the basic configuration of the operational amplifiers. An operational amplifier can be operated in three modes. One is called the differential mode as a differential amplifier, and second is the inverting and the non-inverting operational amplifiers. So the inverting is one. These are all come under the open loop. That means there is no feedback from the output into the input. There is no series of either resistance or any of the element connected between the input and output. So without that, the configuration is known as open loop configuration. Now let us look at the chart. So here under the open loop system, the differential amplifier is a common one, which you know very well already. So now using an operational amplifier, that op amp can be used as an inverting amplifier. Inverting amplifier is one in which the output is with respect to the input, the phase shift is inverted. That means the phase shift of inversion of the 180 degrees. So here now let us see that there are the plus and minus, which are called the non-inverting input and inverting input. Now I am giving a, see, with respect to these signals of plus minus, I am giving a input called Vin, called nothing but from a signal source, and these are nothing but the common or called reference points. And this point is signal source here, and this point is nothing but one of the. So with respect to Vin here, the signal is applied at the minus, called inverting input. And the operational amplifier, generally we are considering the MUA741, and that has got a gain of large signal gain called A. That A is represented as here on the block, and the output voltage is corresponding to, that means V0 is equal to this A of the system are called operational amplifier multiplied by the input signal Vin. So V0 equal to A into Vn, but here there is a minus sign. The minus indicates that there is a phase shift between the input and the output. So with respect to the input here, the minus indicates that it is a inverted. That's why the name is given as inverting amplifier. The second case is here, in this case called the non-inverting amplifier. Now as a similar configuration also is available, but to the place inside of the input terminal called your non-inverting input, I am connecting a voltage source called signal source, whose value is equal to Vin. This Vin is connected to the plus, and the negative or called minus sign of this called inverting input terminal is connected to the ground or common point. Now the voltage existing between these two is called your VID. Now the output voltage equal to these system are called your operational amplifiers open loop are called your large signal gain A multiplied by the input signal Vin. So here V0 equal to A into Vin or Vin. Here there is no minus sign because the signal is connected to the plus of the called your non-inverting, hence the output is equal to simply multiplied by the gain times the Vin. There is no phase shift here. Okay. Now coming to the application part of the amplifiers, we can use it in any way in the mode of your requirement or the electron circuit as it requires. So operational amplifier can be used as a summing amplifiers, as a summer. What is meant by summing amplifier? Whatever the input you connect, the number of the voltage sources, and that is called your say with reference to this figure here, this plus input and minus input both are there. The plus input is here in which the connected to R, and the value of the R is called your R compensation. The value is calculated depending on the values of your R1, R2, R3 in parallel combination, and that value of R is decided and returned to the ground. Now to the negative called your inverting input. Here the number of voltage sources are connected through resistance R1, R2 and R3. These voltage sources V1 will supply a current of I1 through R1 into the circuit. Similarly, V2 will supply a current of I2 through R2 into this, and V3 will supply a current of I3 through R3 into this. So here A is a node, that nodal equation you know very well, and here it will be the current flowing into this is 0, so therefore the voltage effectively is 0. That's why the point A is called virtual ground. The point A is called the virtual ground, and through this now the current flowing is called your IF, and the IF is flowing into this and the output is developed depending on this. Now how the operation amplifier work as in summing, let us see. Now these are the voltages V1, V2, and if I want to calculate this point here with respect to, so there sum of the voltage is equal to V1 by R1, V2 by R3, V3 is equal to sum of the current. Similarly the output here V0 by RF is the current. The current flowing into this equal to the current flowing must be output. So therefore that V0 equal to minus of, because it is inversion here. So because of this minus bracket starts, this voltage divided by the resistance RF multiplied by the voltage will give the current, and the current multiplied by the RF will give the voltage. So the sum of these voltages. Finally the output voltage equal to, of course, minus of RF by R and sum of these voltages. That's why is known as a summing amplifier. And now coming to the second application of your, so these are all comes under what category? Known as under closed loop. Why it is called a closed loop? Because always we are connecting one or either of the element from the output into the input terminals. So the next configuration is called our operation amplifier as a subtractor. So the subtractor in the sense means the voltage whatever you are applying at the input terminal can give you a difference of the voltage in the output. So here with respect to the figure of A, which has got the large signal gain of A, same MUA741 I have taken, any of the general standard operation amplifier will hold good all the discussions, and here now the plus VA is applied to this and my plus VB is applied to this. So the input of this minus has got VA and plus of has got here, means non-inverting is VB and inverting is VA, and I have used the resistance values of R are equal and a feedback resistance is connected, hence it comes under closed loop. So RF is the value of the resistance, and here R is connected whose value is again compensation of all these values which I calculated in the same fashion like this. Now the output voltage V0 equal to this VB minus of VA, hence this acts as a subtractor. Now let us see the continuation of that under closed loop condition which you have seen. Now the third configuration or third type of circuit which can be applied is called your integrator. Operation amplifier can be used as a integration whose function is exactly equal to the mathematical integration of an input function, and also can be used as a differentiator, nothing but a mathematical differentiation of any of the input voltage. Now let us see the figure here. In this case, now this is connected as a operation amplifier as an integrator circuit. Now this from the output to the input terminal which is called inverting input, here the capacitor is connected as a feedback circuit, feedback element, and R1 through R1 it is connected to the V in source. V in source is nothing but a sinusoidal input. So it can be a one of the any of the AC input. So in this case now whatever the input we are applying here through R1 and through this to the terminal. So now the R1 and CF has got a some time constant which is equivalent to 1 second. Now I am applying a input voltage whose output is nothing but a sinusoidal input. The sinusoidal output of this V in which is applied to the circuit is shown here as a input waveform which is called sinusoidal or sine wave. That sine wave has got a period like this 0 to t by 2 t, and the next is the off cycle 3t by 2. T in seconds is the axis, and V here vertical line V in indicates. So the input waveform when it applies to here such a circuit here, it will act as an integrator. So therefore the output waveform of this function will become like this. It starts when it is here and it goes like this inversion and then come. The value of this positive peak is plus 1 and the value of this is negative peak is 1 volt, whereas here this comes to equivalent to minus 1 and minus 2. So therefore it is nothing but a clamping. So the integrator which produces a almost same sinusoidal waveform but with 0 as a reference and goes to the negative peak of this equivalent to 2 times 1 of the peak. This is the output waveform. Now similarly if I apply instead of this function sinusoid, if I apply a called a square wave like this whose amplitude is equal to from 0 to plus 1 positive peak and negative peak minus 1 volt. In this waveform it is nothing but a V in input waveform, and with respect to this here, because of that it has got some time constant of RC, therefore for this pack value here this acts as a simple short circuit, hence output is 0. Hence output is 0 even though it is raised from 0 to here 1 volt within no time, here it is remains same, and it now charges slowly depending on the time constant of R1 and Cf. So therefore it charges like this, and by the time it charges here there is a change in the input waveform, and that waveform is dropping from +1 to 0 level. So therefore it has to come back to 0. Now it has to discharge, or it will discharge not as just like input waveform is fast, but depending on its own time circuit constant called R1 and Cf, it gets here the discharging, and by the time it reaches 0 here again still it is a negative part, so therefore there is no effect on this from -V to 0. So therefore it will continue like this, and again from here it will get discharged. So integration of this is nothing but the output waveform. Hence for a square wave input, this is the response, and the response of the circuit depends on called your frequency response of the circuit FB is equal to 1 by 2 pi R1 Cf at 0 dB gain. So this is the application of the one of the operation amplifier as an integrator. Now coming to the second circuit, under the same closed loop condition, an op amp acts as a differentiator circuit, exactly mathematical performance it does. Now we are applying similar to a sinusoidal wave, what we will get is the output is the cosine wave, because you know very well the sinusoidal differentiation is nothing but a cosine with a negative sign, and here minus Vc plus V supplies are there, and once again to the inverting position only we are applying the input signal through the C. In the differentiator circuit, when compared to integrated circuit, here the R and C positions are interchanged. Now this C1, the current flowing through this one will try to charge through this one, and now for a sinusoidal I said already it is nothing but the same waveform except the cosine, and when compared to this a square wave input voltage here, now refer to the input waveform. This is the input waveform which I am applying to this, to the circuit 741, which is acting as a differentiator. Now during this 0 to 1 positive here, the voltage will be, because it charges immediately and then goes to the -V, and now when here it goes to the positive and then comes, because it is inversion, otherwise it would have been a non-inverting, the similar follows. And whenever, and one more thing also you have to observe here, the peak voltage is 0 to plus, but whereas here it is from 0 to +2 volts, similarly 0 to -12 volts. That means 2 times the input waveform, the spiky waveform is produced, and the spiky waveform gets discharged or gets charged back to 0 is depending on the slope. The slope is decided by the time constant of Rf and C1, Rf and C1, which I said here tau is equal to Rf and C1. So it produces a spiky waveforms. So there is nothing but the differential output of this input waveform called square wave, and mathematically we have shown here V0 equal to minus of Rf and then C1 into dVin by dt. And one thing also you can notice here from this part of, you may also get a doubt here that why it has gone to a -V. Yeah, the reason is in this case, now the reason is in this case here when I refer to the integrated circuit part of it, you can see that it is 0 to -V, when 0 to only half of the voltage, that is depending on this inversion input I said. And suppose if I interchange these connections to the plus and minus, then I will get the waveform for the square wave input here starting with from the 0 to plus side and goes back to this. This is one of the thing. Then here also the frequency, what is meant by FB? FB is the maximum frequency response. That means for any type of variations in the input side, this can produce the correct mathematical expressions, which were shown in case of a integrator V0 equal to minus of 1 by R1 Cf integration of 0 to T Vin dt. So this response is allowed only the maximum frequency response depending on the 1 by 2 pi RC, which is measured at 0 dB of the gain. Similarly, here also this also holds good for the same frequency response FB equal to 1 by 2 pi Rf and C1. Once again here Rf and C1, which is nothing but the configuration of this differentiator, will also hold good provided that it is measured at 0 dB. Then only these circuits will exactly function as equivalent to that of a substitution of the mathematical differentiation. This mathematical differentiation as well as integration will hold good for any of the configurations of the any circuits. And now also you can see many things on this, no doubt. One can also say that how this acts as a differential amplifier. See, basically the input side which you are showing here, minus and plus, in any of the configuration generally when we come, the general configuration whatever we refer is nothing but a differential input. So the input always will measure what is the difference lying between this terminal and this terminal. Whenever it is grounded here, it is assumed to be that it is also be a 0 volt. That's why it is known as a virtual ground. And effectively the current flowing into this is, which was defined as offset current, is almost a 0. So therefore, now the perfect whatever the voltage is there will be getting impressed across the input side without any loss or current flowing into the operational amplifiers. Basically operational amplifier will not take any current into its input terminals. That's why the very best matching they do is CMRR whatever we define has to be very large value, and that is one of the specification which you have to see. And also these topics whatever I could elevate to some extent for the lightness of the students, they can refer any of the standard books, either operational amplifier by G.B. Clayton or any of the Indian version. If you want to study, you can also refer the book operational amplifiers called linear integrated circuits by Ramakanta and Gaikwad, also is available in Indian version. So any of these books will give you a lot of information apart from whatever I have given. And this is the one of the basic amplifier where you can really use in any of your circuit mode of configuration you want to design. Even they can be used as called your scalars. What do you mean by scalar? Depending on your type of the ratio you want to divide any of these input into a number, that can be done. That is done by one as a scalar. So now here basically this can be used as a scalar or a multiplier or a divider or a integrator or a differentiator or any summing or inverting, non-inverting, and as well as a subtractor. Any of the things can be used. So basic operational amplifier is one of the good element or something like a tool in your electronics designing circuits.